Yeah. Let's say our K is 7. So what class would this be? Anyone else want to guess? Yeah, go ahead. Yep, it's going to be class A. So as you can see, our circle is expanded now. And so we're going to get 4 stars and only 3 triangles. So our class is going to change. So as you can see, the value of K matters a lot because it basically determines how this new data point is categorized as. All right, so let's talk about some applications that KNN has in the real world. So KNN actually is pretty common in a lot of daily things. So one of the things is recommendation systems. So let's say like you and your friend are watching like a Netflix show, right? And so based on the algorithm, you and your friend are essentially similar. You guys are neighbors because you guys have a lot of similar interests. And so by the algorithm, you guys are considered similar data points. So as a result, in the future, any show that you watch is more likely to be recommended to your friend by the algorithm. And this isn't just for Netflix, it's for like Amazon, like, stuff that you buy, or, Prime, Hulu, etc. It's very common for many recommendation systems. Another thing is image recognition. It's really good for, again, classifying images and, figuring out, is this picture a dog? Is this picture a cat? It's a very basic application of KNN, but it's pretty important. And another one is anomaly detection. So like, since KNN is really good at recognizing like patterns, so let's say you get like a spam email, it's very good at finding out what features make it a spam email. And so you can recognize whether another email is also a spam email or not a spam email. So it's very good for those kind of classifications. Again, these are just a couple applications of KNN. There are a lot more applications, but these are just kind of some of the most important applications of KNN. Yeah. Okay. So KNN obviously has some advantages. The one thing is it's a pretty simple algorithm. It's pretty easy to implement. So it makes it very sought after, very popular. It can be used for both regression and classification problems. I'm mainly talking about classification problems in this presentation, but it can be used to solve regression problems, especially since it's really good at pattern recognition. Another thing is that it doesn't require model training. Again, it runs straight off the data set. So you don't need to put it through a training stage, and it's not super resource heavy. Another thing is, since it runs straight after the data set, it easily adapts to any changes in the data set because, again, like if you introduce a new data point to the data set, it's going to recalculate the distance from every point that's already in the data set. So it's going to start new. And so any changes you make in the data set will affect the new data point you want to categorize. So KNN also has a couple of disadvantages. The fact is that since it runs directly out off your data set, if your data set is really large, it can get a little slow. And it has to store the entire data set, so it's going to use up a lot of memory. So those are some drawbacks. Also, if your data is inaccurate, then again, classifying new data points is also going to inaccurately classify those data points. So again, it's very important to have data that's accurately classified and not imbalanced so that you don't have bias or irregular performance. All right, so let's get into a little bit depth of like what the steps are and how KNN actually works. So let's go through the first step. So essentially what you're going to do is you're going to start off with a coordinate plane, right? And your coordinate plane should already have the data that's already labeled. You need labeled data. And then you're going to need to introduce your new unlabeled data point into that space. Then you're going to need to calculate the distance from all the points, from the point that you want to label. And you're going to choose your value of K. And after you choose your value of K, you kind of want to check, what are the K nearest neighbors? What are the K nearest data points? And you want to assign that data point based on the majority vote and assign that to a new class based on that. So step 1, populate your space with labeled and unlabeled data. So let's take a look at the example right here. I've got 3 classes. So this is a multi-class classification. And so I've got yellow, green, and orange, and that's my data. That's my coordinate space. And I'm introducing my little gray data point because I want to classify that into one of those classes. And so I've got step one. And now I need to calculate the distance. I need to know exactly how far the rest of the data points are from the new data point I introduced. So there are a multitude of different formulas that are used in KNN, but one of the most popular ones is Euclidean distance. Euclidean distance is used when data is in continuous geometric space. And what do I mean by continuous geometric space? It's a space where the values are continuous. It's not discrete values. You have continuous data. Manhattan distance is also another popular formula. It's better for higher dimensional spaces and more grid-like data because Euclidean distance can get a little, iffy once you go beyond like a certain dimension. And finally, we've got Hamming distance. Hamming distance is good when you have data that's the way you want to basically magnify to either a 0 or a 1. It's very good for mismatched data, like you want very extreme data. So it's very good for like, let's say, text classification. So it's either right or it's either wrong. There's no in between. So let's go a little bit into why Euclidean. Why is Euclidean so popular? How do we do Euclidean? What does it even matter? Well, the thing is, you guys actually already know Euclidean. So let's say I have two data points right here. I got these two data points and I have this little yellow line that's connecting the two data points. And I want to know the distance. I want to know the length of that yellow line. Well, let's draw a little triangle and I've got A, B, and I want to know the value of C. So what formula would you use to find C? Anyone want to answer? Yeah? Yeah, exactly. Pythagorean theorem. It's literally, yeah, it's as you said, a squared plus b squared, square root the whole thing, and that's the value of C. So Euclidean is basically just Pythagorean theorem, but you're extending it across all dimensions. You're increasing it. Pythagorean is only applicable towards 2D coordinate plane. But if you extend it, you get Euclidean. And so basically, you notice in this 2D plane, you just have an X and a Y. But when you extend it to like n dimensions, you add more values. For example, in 3D, it would be an X, a Y, and a Z. And then it goes on and on for 4D, 5D, etc. So we get two data points, and we have P1, P2, all the way to Pn, and Q1, Q2, all the way to Qn. This is for n dimensions. And what you're basically doing is essentially the same thing as Pythagorean. You're taking the associated values, Q1 minus P1, you're going to square it, you're going to add up all those distances and then square root the whole thing. And that's essentially just the distance between two data points in n-dimensional space. This is a straight line distance. So it's essentially the same thing as Pythagorean. It's a straight line as the crow flies distance between 2 points in n-dimensional space. And that's how you do Euclidean distance. All right, so now that we've calculated the distance between the unlabeled point and all the labeled points, well, we got to choose K. But what do you guys think is some important factors we need to consider when we choose K? Anyone have any ideas? Yeah. Anyone? All right, let me give a little hint. Think about what you would want to avoid. If you have two classes, what would be a value of K that you might want to avoid? Yeah. Exactly. Perfect. Yeah. So you want to avoid ties because, again, if you have two classes and you're going to get like, let's say you have two classes and you have a K value of 2, there's a possibility that you're going to get 1 point in one class and 1 point in another, and then that's not going to be fun. So usually for binary classification, which I described earlier, it's two classes. You're trying to categorize between two classes. You want to usually use odd values. So 1 and 3 is very common as a value of K. And for multi-class, I would suggest thinking about divisibility. So let's say you have like 3 classes, I would probably avoid the value of 3 for K. If you have 9 classes, I would still avoid the value of 3 again, because 9 is divisible by 3. Another thing is considering data set size. So you might want to use a larger K for a larger data set, which kind of makes sense, right? You want to make sure that your K value doesn't cause bias, because if your value of K is extremely small for a large data set, there are some classes that you might be ignoring or some data that you might be ignoring, and that could always cause bias. So think about trying to keep your K value proportionate to your data set size. All right. So now that we know how to pick the value of K, we've got our 3 classes, and I decided to pick the value of 4 for K so that I would avoid that tie. And as you can see, we're going to get 2 yellow, 1 green, and 1 orange. And so we can go to the final step. It's voting time. The pun is not intended. So now we can check how much of each is in how much of each class is in your neighbors. So you get 2 yellow, 1 green, and 1 orange, as I said earlier. So as a result, yellow wins, and our new data point is of the class yellow. And so yeah, that's basically essentially how KNN goes in depth. So here's a quick demo of how new points get classified. As you can see, this based on the neighbors, you're getting red points, blue points. It's just a little GIF that I thought looked pretty cool. All right, so I think we'll go through one final example. Again, it's about voting. The pun is not intended again. But based on the value of K, I want to see if you guys can classify this question mark one more time. So let's say our K value is 5. What class would this question mark be? What party would we be voting for? Yeah? Yep, that's right. But let's say we expand our K value a little bit. Let's do K equals to 10. What party would we be voting for now? Anyone? Yeah? Yeah, still party B or party 2. Yeah. I guess I'm winning. But yeah, so that's essentially it for my description of the theory of KNN. Let's try to get into the application and let's see if we can program it. So here's a link and just.
Actually, before we get into the coding, does anyone have any questions about the confusion, about how it works, about what you would do? And actually, there is one thing I did want to mention, because we talked about trying to avoid ties with the number that we set K to. We're not going to be able to avoid ties all the time. We could set K equal to 50, and we could get, well, and there's like 20 classes, K equals 50, that should avoid ties, hopefully. Looks like we got a 25 and 25 even split between 2 classes. That sucks. What do we do? Well, generally, we will either just pick randomly or go with the one that appears most in the data set. You try to avoid ties, but sometimes you're going to have them, and you just essentially pick one of them. That's really all you can do. Yeah. Any questions about how it works, anything like that before we move on to code? No? Okay, cool.
All right, cool. I'm just gonna open up the Colab real quick. Just raise your hand if you can't open up the Colab for some reason.
Don't forget to make a copy.
Yeah.
Remember that.
Yes, please.
To make save your changes.
All right, so yeah, this is just how the Colab should look like. Make sure to go to File here, and you can save a copy in Drive to make your copy. Does everyone have their copies? Everyone set? Just give me a thumbs up.
Still getting it set up.
All right, cool. So I guess we can get started. So essentially what we're going to be doing is we're just going to kind of simulate the KNN algorithm in this Colab. So we're getting the iris data set, and we're just going to start off by just looking at the structure of this data set. So we'll just run the first cell right here. And as you can see, we have a little data set here, and we have three classes. We've got, if I remember right, it was like Virginia's with something else. We got three classes here. And we can see the features that we're based on. We got based on the petal length and the petal width. So that's what we're classifying these flowers based on.
Mention something. We've used the this is I think it's called the iris data set a couple of times, but I don't think we've ever really covered specifically what it is. So just as a little mini explanation, these are flowers. Each data point is a flower, and it is one of three types. Right now, we're just showing them as black, gray, and yellow. So there's three types of flowers. We're seeing that. Let's call them black flowers, yellow flowers, and gray flowers. Each flower has a bunch of data about it. So the sepal length, which I think is the petal length, and then the sepal width, which is the width of the petal. So we're going to take a flower, we're going to check the petal width and the petal length, and then we have the output, which is the type of flower. So this flower is a type black flower with a petal length of 4.5 centimeters and a petal width of about 2.3, 2.4 centimeters. So just to get an understanding of what we're looking at when we use this data set, which we have a couple of times actually. So I wanted to clarify that.
Cool. Thank you, Kevin. So now that we see our little graph, we can go over to the next cell right here. And so here we have the Euclidean distance function. So as I said earlier, Euclidean distance is very commonly used to calculate distance in KNN. And so I was wondering if you guys could try seeing if you can program how the Euclidean distance formula. Okay, I'll give you guys like a minute and then maybe we can check in and we'll go over it. Yeah, okay. So Kevin's going to be writing the Euclidean distance formula for you guys, just in case you guys need a little help with it. Is there that? Okay. Should I just show them the master or should I like? Oh, cool. All right. So does anyone want to like volunteer and suggest, any ideas on how to program this function? Yeah. Yeah, that's right. So I'm just going to be programming this out for you. All right. So what we're going to do is we're going to start off with a little for loop. So we don't know the length. We don't know what dimension exactly this might be in. So what I'm going to do is I'm going to program this through the and we're going to iterate through every coordinate in each point. So this is going to iterate through every coordinate in each point, and we're going to be, since we do repetitive actions for each associative coordinate. So first we're going to start off with, finding the difference between the two. So we're going to do, we're going to take the P1 coordinate, and we're going to subtract that by the P2 coordinate. What do you guys do? What do you do after you subtract? Yeah. Yes, you square it. Yep. And what do you do after you square it? Anyone? Yeah. Yep. You find the square root. So I'm just going to be returning the square root of the distance. So I'm going to put this to the power of 0.5 because putting it to the power of 0.5 or power of 1/2 is the same as square rooting it. So, oh yeah, good. Yeah. All right. So now that we run it, we're going to run it and we have our two functions. So this is a Euclidean distance function. That's what we just programmed. I also have a voting function, and this is just to find the value in an array. And we're just going to find the value that has the most because we just need the majority vote. So now that we run that, what we're going to be doing is we're just going to be splitting our data into the unlabeled data and the labeled data. So we're going to need to categorize the unlabeled data based on the labeled data. And so in this little demo, we're just trying to guess one flower, and this is a virginica. So we're just going to try guessing that one. So now that we have the distance function, we essentially just call it for every single unknown flower and known flower, and you just loop it. So this is a for loop where you're just looping it and you're trying to save each distance because it's just very tedious to calculate the distance every single time. And as you can see, for each flower, you get the distance from your unlabeled point, and you get the type of flower it is too. All right. So now that we know all the distances between known and the unknown flowers, we can sort them by distance. So we can just basically sort them from closest to furthest, and then we can just look at the first k closest distances, and we can just look at those flowers. So for our sake here, our k value is 10, but there's a cell later where you guys can adjust the value of k to optimize it. So here, so based on k equals 10, we're guessing the flower is a virginica, which is right because when we look earlier, our unknown flower was a virginica. So this was classified correctly. Now we can put that all together, and basically what this does is it basically calls all the functions together and runs it. It just iterates through the entire data set, and we just run it through the entire unknown data set. I do have a couple different functions here for different distances. I have Manhattan and Hamming. You guys can change the code and see if you guys can optimize it by just calling a different distance instead of Euclidean. All right, so this is where I want you guys to play with it a little bit. And I want you guys to see if you guys can find an optimal K to reduce this error percent as much as possible. So I'll give you a minute. Just try to play with the value of K. Try to find a smaller K value that might optimize the error. So I think for 10, I think it was an error value of like 3.4. Try to find an error value that's a little less than 3.4. See if you guys can figure that out.
Also, we have the distance metric right here. If you could highlight that line. If you scroll up from here, you can see some other distance metrics. So if you want to change that line, instead of saying distance metric equals Euclidean distance, you can change it to say distance metric equals Hamming, distance metric equals Manhattan, or distance metric equals my distance. And you're welcome to try and create your own distance function just to try it out. You can create whatever you want, but we have the ones that we went over here as well. I will say the one thing you should note is that P1 and P2 are each arrays. Oh, I left the marker. I'm going to write this on the board. But when you're creating your own distance function, P1 and P2 are both arrays. And I'm about to show you how to access their indices, just in case you forget.
So as you can see here, putting Hamming distance kind of changes the error value, as you know, Hamming distance and Euclidean distance are better for different kinds of data sets. So please take a look at that.
So in your code, how you access the X and Y values you want to do. You're learning your distance function. Also, has anyone gotten below a 4% with the K values? Raise your hand. Okay. Okay, has anyone got below a 3% with the K? Raise your hand. Oh, nice. What K value did you use? 13. What percent did you get? I got 10. Nice. Anyone else? Yeah. 15. And what percent did you get? Nice. 13. 15. Oh, nice. And then we have one more in the back. Did you raise your hand? Nice. Okay, cool. So 15 and 13 sounds like they give pretty good values.
Yeah, I mean, I got a 15 as well. Yeah. All right. Yeah, so keep trying to play with it and see if you guys can get below me. I got a 2.93.
And so yeah. Can you go to the back to the slides? Do you have anything else? Okay. That's the end of the meeting, everyone. Thank you all for coming. Feel free to sit here. We'll be here until 5. So, if you want to keep trying, see what else you can do, try your own distance functions, or just have questions, we'll be here. If you could give some feedback on this lecture, that would be great. We have just a short Google form. Here's the Discord, the link tree as usual. Thank you all for coming, and I hope this was a little more easy to understand than some of the other ones. Difficulties or topics range in difficulty. But yeah, thank you all for coming, and I'll see you guys next meeting. Or there's also the Sky's No Limit workshops on Fridays.
It's kind of cut off on the slides there, but the link to the feedback form is tinyurl.com KNN-feedback. So please give us some feedback if you can. It helps us a lot. Thank you. Yeah, I can end that.